Okay, hello everyone. My name is Francisco Falcon. I'm an exploit writer for Core Security, and I'm here to present this talk, which is called Breaking Out of VirtualBox through 3D Acceleration. And this talk is about the internals of the 3D acceleration feature of VirtualBox. It's also about 3 memory corruption vulnerabilities affecting the 3D acceleration feature and how to exploit them in order to escape from the VM and execute code on the host. First, a few words about me. I'm an exploit writer for Core Security. I'm from Argentina. I'm interested in reverse engineering, exploiting, and etc. And also, this is my second time presenting here at REcon. So, this is the agenda for this talk. First, a few words about the motivations and related work. Then we'll take a look at the internals of the implementation of the 3D acceleration feature, including the VBox, HGCM, and Chromium protocols. Then we'll see what are the Chromium rendering commands. After that, we'll be ready to uncover 3 memory corruption vulnerabilities affecting this feature, how Oracle fixed them, and then we'll go to the fun part, which is the exploitation phase, in which we'll see how to exploit these vulnerabilities in order to escape from the VM. And we'll finish this presentation with a live demonstration of the guest-to-host escape. So, the main motivation for this work was a blog post by Tarjei Mant, who described memory corruption vulnerabilities affecting this 3D acceleration feature of VirtualBox. So after reading that post, I decided to keep working, trying to find vulnerabilities in this code and try to exploit them in order to escape from the VM. And if you're interested in this topic, here you have a brief and really incomplete list of related presentations which describe attacks against hypervisors like VMware, KVM, and Xen. So, VirtualBox is a virtualization software which focuses on virtualizing Intel x86 hardware. And it runs on different host operating systems, and it supports a bunch of operating systems inside the virtual machines. And among many features, VirtualBox offers a feature which is called 3D acceleration. This feature will allow an operating system running inside the virtual machine to use the 3D graphics hardware, which is available on the host, in order to do fast rendering of OpenGL graphics. And the implementation of the 3D acceleration feature depends on the VirtualBox guest additions, which are a set of tools that you can install on a guest in order to improve its usability. Also, this feature must be manually enabled. So, when you install the guest additions into a guest system, you are installing a driver which is called VBox guest, which uses port-mapped input-output in order to communicate with the host. And this is an interesting warning that you can find in the online documentation for VirtualBox. Basically, they are telling you that enabling the 3D acceleration feature for untrusted guest systems may put the security of the hypervisor at risk. They know that the code that implements 3D acceleration is huge and also complex, so they are afraid that the bugs in that code may be used to crash a virtual machine. However, we are going to see during this talk that the bugs that are present in this code can be used to do way more than just crashing a VM. In fact, we'll be able to escape from the VM and execute arbitrary code on the host. So, the Chromium library. VirtualBox uses a library which is called Chromium in order to provide this 3D acceleration feature. Chromium is an open source library which is not related at all to the famous web browser, and the purpose of this library is to perform remote rendering of OpenGL 3D graphics. This library has a client-server architecture. A Chromium client is an application trying to render OpenGL graphics inside the virtual machine, while the Chromium server runs on the host side in the context of the hypervisor. And on the client side, the Chromium client works like this. Basically, it replaces the native OpenGL libraries with its own interception library. This way, it will capture all the calls to OpenGL functions, and they will be converted to a serialized form. This is a stream of Chromium rendering commands, which in fact is a type of bytecode, which is composed of opcodes plus data for those opcodes. And those rendering commands will be sent from the Chromium client inside the VM to the Chromium server in the host side over some kind of protocol. In fact, VirtualBox added support to Chromium for a new protocol, which is VBox HGCM, which stands for Host to Guest Communication Manager. This protocol will allow the Chromium client inside the VM to send data to the Chromium server on the host side. And this protocol works through the VBox guest driver, which is part of the VirtualBox guest additions. So this is a graphic that I did about the architecture of all of this. We have the host side on the bottom with the hardware, including the 3D graphics card, the host OS, and the user mode VirtualBox hypervisor. And as you can see there, the VirtualBox hypervisor has the Chromium server loaded into it. On the guest side, we have the guest OS with the VBox guest driver loaded. And on top of it, we have any application trying to render OpenGL 3D graphics inside the virtual machine. Those two DLLs that you can see on the application are part of the interception library of Chromium. They will capture all the calls to OpenGL functions and convert those calls to a type of bytecode, which are the Chromium rendering commands. So the interception library will send that rendering commands to the VBox guest driver, and the VBox guest driver will forward that data to the Chromium server on the host side, and the Chromium server will do all the heavy rendering of the OpenGL 3D graphics by using the 3D hardware. So let's see how we can speak the VBox HGCM protocol in order to communicate from the guest side to the host side. This is the first step. This is really simple. We need to obtain a handle to the VBox guest driver from the guest side. So we call the create file function, and we don't need any special privilege in order to open a handle to this driver. The second step is to send a message to this VBox guest driver by using the device IO control function. And this VBox guest driver supports a bunch of IO controls, but we are going to focus only on the three ones which are highlighted in red. They are HGCM connect, HGCM call, and HGCM disconnect. This is how a Chromium client running inside the virtual machine can connect to the 3D acceleration service, which is exposed by the Chromium server. It will need to call device IO control in order to send an HGCM connect message, and it will specify the name of the 3D acceleration service in the input buffer. The name of the acceleration service is VBox share CR OpenGL. So that's the VBox HGCM protocol, which is generic and it's pretty simple. And let's see now how we can speak the Chromium protocol, which goes on top of the VBox HGCM protocol. The 3D acceleration service of the Chromium server, exposes a number of functions that can be remotely invoked from the virtual machine, and they are enumerated there. For example, fnwrite, fnread, fnsetPID, etc. And this is an example of how an application running inside the virtual machine can send an HGCM call to the driver in order to remotely invoke a function from the 3D acceleration service. It will send an HGCM call IO control, and in the top side you have the input buffer. In red, that's the function that we want to remotely invoke, then the number of parameters we are sending, and finally in green, the parameters themselves. So basically, when an application running inside the virtual machine sends an HGCM call message to the driver will do three things. First, it will copy the input buffer from the guest to the host. Then it will perform a call to host-side code. And finally, it will copy the results from the host back to the guest. And this is how a Chromium client can start a communication with the Chromium server, which runs on the host side. First, it needs to open a handle to the VBox guest driver. Then it sends an HGCM connect message. And after that, it will need to send 2 HGCM call messages in order to invoke 2 functions from the 3D acceleration service, which are fn set version and fn set PID. After that, the communication between the client and the server is successfully established. So now the Chromium client can start sending all the HGCM call messages that it needs in order to invoke all the functions that it needs from the 3D acceleration service. When it decides to close the connection, it will send an HGCM disconnect message and then just close the handle to the VBox guest driver. So we already talked a bit about the Chromium rendering commands. When a Chromium client converts the calls to OpenGL functions to rendering commands or bytecode, they are sent to the Chromium server. The Chromium server will process that bytecode and store the results into a frame buffer, and then the frame buffer will be transmitted back to the guest. This is how the CR message opcode structure looks like. This is the structure that is used to send rendering commands from the guest to the host. It has a type field indicating that it's CR message opcodes, another field specifying the number of opcodes that are being sent, then the opcodes in reverse order, and finally the data for each one of the opcodes. And that data can have a different length. So this process of sending rendering commands or bytecode from the Chromium client to the Chromium server can be done in 3 ways: single-step mode, 2-step mode, or buffered mode. In the first one, the Chromium client will send rendering commands to the server. The server will process them and return the resulting frame buffer in one single step. In 2-step mode, the Chromium client sends rendering commands to the host. The host processes those rendering commands, and then the client needs to send another message requesting the resulting frame buffer. And the most interesting one is buffered mode. This buffered mode works like this. The Chromium client will send rendering commands to the Chromium server on the host and say, hey, wait, I'm sending you these rendering commands, but don't do anything with them. Just store my data on a buffer and wait until I send you another message requesting you to process my bytecode. So, as you may guess from this description, this buffered mode will allow an application running inside the virtual machine to allocate an arbitrary number of buffers with arbitrary size and containing arbitrary data in the context of the hypervisor process that runs on the host. So that's basically a way to perform heap spray remotely from the virtual machine in the context of the hypervisor process. So please keep this into mind, because we'll make use of this later when we focus on the exploitation phase. So when the Chromium server receives rendering commands or bytecode, it will call a function which is called CR_unpack, which is basically a bytecode interpreter. This is the code of this CR_unpack function. Basically, it will traverse the received opcodes and call a function to handle each one of the supported opcodes. This is really a simple interpreter. So that's the basics of the implementation of the 3D acceleration feature of VirtualBox. So now we are ready to uncover 3 memory corruption vulnerabilities that affect the Chromium server that runs in the context of the hypervisor on the host side. So, look, this is a function that belongs to the Chromium server that is handling 2 different message types: CR message writeback and CR message readback. And it turns out that those 2 message types are the implementation of the so-called Chromium network pointers. If you read the documentation of Chromium, you'll find that they say that network pointers are just memory addresses that reside on another machine. And the networking layer of Chromium will write the payload data to the specified address. So I guess right now you're saying, what? It is for real? And yes, this is for real. So here it comes, the first vulnerability. This is the function that handles the CR message readback message type. The attacker from the virtual machine fully controls both of the parameters for this function. And as you can see there, highlighted in red, there's a memcopy operation, and the attacker from the virtual machine controls the destination address, the source address, and even the size for this memcopy operation. So here we have a really powerful write-what-where memory corruption primitive, which is the result of a really gross design error, the so-called network pointers, and it will allow an attacker running inside the virtual machine to write any data to any memory address within the address space of the hypervisor. The second vulnerability is closely related to the first one. It is also the result of the network pointers. This is the function that handles the CR message writeback message type. In this case, the attacker from the virtual machine fully controls the only parameter for this function. And as you can see there, highlighted in red, the attacker from the virtual machine can decrement the value stored at any memory address within the address space of the hypervisor. So here we have another memory corruption vulnerability, which is also the result of the network pointers. So it will allow an attacker to modify any memory address within the address space of the hypervisor. The third vulnerability is not related at all to the network pointers. When a Chromium client sends an opcode OXEA, the Chromium server will call the CR unpack function, which is the bytecode interpreter, and it will call the function that handles that opcode. This is the code of that function. It uses the read data macro, which is a macro to read data that is fully controlled by the attacker from the VM, and it will call another function passing as parameters 5 values which are fully controlled by the attacker. So let's see the other function. Look, it's writing there where it's highlighted in red, it's writing the CR unpack data variable, which is a pointer to data fully controlled by the attacker from the VM, to that array. And they forgot to check if the index parameter is within the bounds of the array. So here we have another memory corruption vulnerability that will allow an attacker from a VM to write a pointer to attacker-controlled data to any memory address within the address space of the hypervisor. And it's interesting that this third vulnerability doesn't only affect the opcode OXEA. In fact, it affects the function that handles all of these 13 opcodes. So, the fixes. How did Oracle fix these vulnerabilities? In the case of the two first vulnerabilities, that is the vulnerabilities related to the network pointers, they added this extra if-def statement, which basically is removing the support for network pointers from the code that runs on the host side. And in the case of the third vulnerability, they modified the Python script that generates the vulnerable C code, and they added this extra condition. Now they are checking that the index is within the bounds of the array. So we have uncovered 3 memory corruption vulnerabilities. Let's see how to take advantage of them in order to escape from the virtual machine and execute arbitrary code on the host. So one of the first vulnerability is really powerful, and it looks pretty ideal for exploitation purposes because it's a write-what-where memory corruption primitive. However, if the host OS has ASLR, we have to solve a problem, and that is where to write to. Well, so here it comes, the third vulnerability to the rescue. If you remember the vulnerable function, it's an indexing error. And it's writing a pointer to attacker control data to an array that belongs to the CR server variable. CR server variable is a global variable that holds a lot of information about the whole state of the Chromium server. So, since this is a global variable, it's located inside the data section of the DLL, which is called bbox, share, something complicated. And since this is an indexing error, the destination address for the memory corruption is relative. This is not an absolute address. So that means that we can safely corrupt any memory address belonging to this DLL without having to worry about ASLR moving this DLL. So far, by sending an opcode OXEI with a specially crafted index parameter, we are able to overwrite any memory belonging to this DLL with a pointer to our data. So the question is there anything interesting to overwrite? Well, one of the many fields of the CR server global variable is a field which is called head SPU, which is a pointer to a SPU structure. And this pointer stored at crserver.headSPU is dereferenced when processing certain opcodes in order to access a dispatch table field, which is a table of function pointers. Look, this is the code that handles opcode OX02. It will dereference the head SPU field, which we can overwrite by using the third vulnerability, and then it will call a function pointer. So basically, that's all we need to gain code execution on the host. The first step is to send an opcode OXEA with a specially crafted index argument in order to overwrite the head SPU field of the CR server global variable. This way, we control the table of function pointers. And then we send an opcode OX02, so a function pointer controlled by us is called, and that's it. Then we are able to hijack the execution flow of the hypervisor. However, probably now you are wondering, but what about ASLR on the host side? Well, both the 4.2 and 4.3 branches of VirtualBox ship a DLL with different name, which is compiled without support for ASLR. So they are loaded at fixed addresses, as shown there. So you can use those libraries in order to build your rob chain and escape from the VM. However, well, that was released, right? However, let me show you this screenshot of Process Explorer running on the host side. Highlighted in yellow, you can see the bbox REM32 DLL, which doesn't have support for randomization, and however, it was relocated. The Windows loader decided to move it to another base address. And so the problem is that you can't always rely on non-ASLR modules because they can be loaded at another address other than its preferred base address if its preferred base address was already taken by another module, right? So let's see how we can write an exploit with full ASLR bypass, that is, not relying on a module being loaded at a fixed address. So, at this point, please let me quote Halvar Flake, who said that info leaks are made, not found. If you remember, the CR server global variable holds a lot of information about the state of the Chromium server. And one of those fields is called clients, which is an array of pointers to a CR client structure. And the CR client structure contains a field which is called con, which is a pointer to a CR connection structure. And if we follow that, we have the CR connection structure, which has two really important fields, which are phost buffer and cvhost buffer. Phost buffer defines the address, and cvhost buffer defines the size of the frame buffer that will be copied from the host to the guest after the Chromium server has finished processing rendering commands. So, as you can imagine, if we manage to control the address and the size of the frame buffer, we'll be able to read any memory belonging to the hypervisor from the guest side, that is from the virtual machine. So the exploitation plan is like this. By using the third vulnerability, we can override the first element of the client's array with a pointer to our data. So our data will be interpreted as a fake CR client structure. The second D word of our fake CR client structure will be interpreted as the con pointer, which points to a CR connection structure. So we could make that conf field point to an arbitrary address, and the idea is to put a fake CR connection structure at that address, so we control the phost buffer address and the CB host buffer size of the frame buffer that will be copied from the host to the guest. In a graphical way, here we have the DLL. In red, you have the CR server global variable and the client's array. By using the third vulnerability, we can override the first element of the array with a pointer to our data. So our data will be a fake CR client structure. And that fake CR client structure has a conf field. So the idea is to make the conf field point to an arbitrary address, in this example 2D0000, and we need to put our fake CR client structure at that address. So we control the phost buffer address and the CB host buffer size that define the frame buffer to be copied from the host to the guest. So the problem that we need to solve is that we need to put some arbitrary data, that is a fake CR connection structure, at an arbitrary address within the address space of the hypervisor. How can we do that if there is ASLR on the host side? Well, here it comes the heap spray technique I told you before to the rescue. Remember that when sending rendering commands in buffered mode, we were able to allocate an arbitrary number of buffers of arbitrary size containing arbitrary data in the heap of the hypervisor that runs on the host. So this is a powerful manipulation technique that will allow us to put our arbitrary data at arbitrary addresses within the address space of the hypervisor. This is a screenshot of the memory map of the hypervisor after I have remotely performed heap spray from the virtual machine. As you can see here, I was able to allocate multiple 1 megabyte buffers, and the buffers are contiguous, that is, there are no gaps between the buffers. So now I have a predictable layout on the heap of the hypervisor. So I need to put my arbitrary data, that is my fake CR connection structure, at a known address. There are two ways, as you can see here, and of course I went the lazy way. That is allocating multiple 1 megabyte buffers and then writing my fake CR connection structure by using the first vulnerability, that is the write what where primitive. So when the Chromium server finishes processing my rendering commands, it will reach this code in which it will copy the frame buffer defined by phost buffer address and CB host buffer size from the host to the guest. So at this point, we already have control over the phost buffer address and CB host buffer size. That means that we have created a really powerful information leak that will allow an attacker from the virtual machine to read any memory belonging to the hypervisor process. However, we still have a problem to solve, and that is where to read from. Remember ASLR on the host side. So one of the many fields of the CR server variable is called barriers, which is a pointer to a CR hash table structure. And these barriers fields is dereferenced when processing the opcode OXF7 with sub-opcode OX08. And this is the function that handles that combination of opcode plus sub-opcode. Making a long story short, the attacker controls both of the parameters for that function call, and we can make that function to return an arbitrary pointer, which is stored in the barrier variable. And in the next line, the code will copy the value of the rank queue field of the CR server variable to an address that is fully controlled by the attacker from the VM. So at this point, basically, we have managed to store the pointer crserver.runq, which is a pointer to a runq structure, into a known address within the address space of the hypervisor. So now we have something interesting that is a pointer stored at a known address within the memory of the hypervisor. So now we are ready to leak it to the guest side by doing all the procedure I explained before. In a graphical way, this is what we are doing. There you have the library with the crserver global variable in red. And by doing the steps I explained before, we are able to leak the value of the runq pointer, that is the first pointer, to the guest side. And this first pointer we are leaking points to a runq structure which is located on the heap. Now we can repeat the whole process in order to read the value of the client field of this structure. So now we are leaking a second pointer which points to a CR client structure also located on the heap. We can repeat the whole procedure for a third time in order to read the value of the current CTX info field. And this third pointer we are leaking points to the main context info field of the CR global variable. That means that this third pointer we are leaking is an address belonging to this DLL. So now we have an address that belongs to a DLL. That means game over for ASLR on the host side. We have leaked an address belonging to this DLL with a difficult name, so that's all you need to start building your ROP chain. And that's it. You have leaked a memory address belonging to a DLL. Now you can build your ROP chain, and I have already explained how to modify the execution flow with a hypervisor by sending an opcode OXEA with a craft index parameter, etc. So that's how you can escape from the hypervisor. But that's enough talk. Let's go with a live demonstration of the guest to host escape. Here I have Oracle VirtualBox, still vulnerable. I have the vulnerable version. So I'll start this Windows virtual machine. And while it's booting, let me show you Process Explorer on the host side. The process that you can see there highlighted is the user mode VirtualBox hypervisor. And this is the process in which we are going to exploit the memory corruption vulnerabilities. If we take a look at the list of loaded DLLs, we can find here, this is the VBox Share CR OpenShield library, which is part of the Chromium server. And the three vulnerabilities I explained before are located inside this DLL. This DLL does have support for ASLR, and by doing all the information leak procedure I explained before, we'll be able to leak its base address in order to build a ROP chain and then escape from the hypervisor. So let me log in here. So right now I'm going to run my exploit inside the virtual machine. Let me find it. Here it is. So I'm going to write my VMscape exploit inside the Windows virtual machine. And if everything goes well, I'll be able to escape from the VM and execute a calculator on the host side. So let's cross fingers. Here we go. And that's it. We have escaped from the hypervisor. So the calculator is now running on the host system. So back to the slides. So, future work and conclusions. It would be nice to try to exploit these vulnerabilities on a 64-bit host OS. In fact, I did it on a 32-bit OS on the host side. Also, it would be interesting to write the exploit for other combinations of guest OS and host OS. And it would be really, really nice to work on process continuation. That is, that the hypervisor keeps running after exploitation. I didn't work on this. That's why after executing the calculator, the hypervisor crashed and went off. So conclusions. First, VirtualBox added a library that is loaded in the context of the hypervisor, and I think that without thinking about its security, it looks like they didn't read the documentation of Chromium, quoting the network pointers. Another conclusion, having a bytecode interpreter running inside the hypervisor doesn't look like a good idea. It's processing untrusted bytecode coming from the virtual machine, and it gave me a lot of flexibility for exploitation. And it's a bit worrying that sometimes even benign OpenGL applications, when the 3D acceleration feature is enabled, sometimes they even crash the virtual machine, and they are legit applications. That's really worrying. So if you visit the advisories page at the core security website, you can find a proof of concept for the 3 memory corruption vulnerabilities. So I hope that by applying all I explained here, you can write your own BAME exploit based on that proof of concept. So this is my contact information in case you want to discuss something. There you have my Twitter account and also my email address. So if you want to write me something, that's welcome. So basically, that's it. Do you have any questions?